Hello, myself Arav Patel, roll number 23 BME 106, welcomes you to the CFD based simulation project focused on verifying Bernoulli's principle using a Cessena 172 aircraft model. The simulation was conducted on software SimScale under steady state incompressible flow conditions. Air was used as a working fluid with a density of 1.225 kilograms per cubic meter and a dynamic viscosity of 1.81 into 10 to the power minus 5 Pascal seconds. The inlet velocity was set to 23 meters per second, while the outlet boundary was defined as a gauge pressure of 0 pascals. A no-slip wall condition was applied to the aircraft surfaces and slip conditions were used for far-field boundaries to reduce computational drag. A fine curvature refined mesh ensured accurate results near the airfoil surfaces, and the K-epsilon turbulence model was chosen to simulate the turbulent nature of the external airflow. The simulation captured key flow features including high velocity regions over the upper wing surface and low pressure zones. To verify Bernoulli's equation, we selected several points along the airflow streamline and extracted pressure, velocity, and height values. We then calculated the total head at each point, the sum of pressure head, velocity head, and potential head, and observed that despite minor variations due to turbulence and viscous effects, the total energy remained approximately conserved. The numerical result strongly supports the validity of Bernoulli's equation under realistic aerodynamic conditions. The Reynolds number calculated based on the wing chord and free stream velocity confirmed turbulent flow lying in the range of 10 to the power 5. We noted that mesh refinement near boundary layers and adjustments to the angle of attack could further improve the flow accuracy and lift grade generation. With this foundational simulation complete, let's now explore the full methodology, visuals, and data insights in the detailed presentation ahead.
Stimulate airflow over Cessena 172 using CFD tools and verify Bernoulli's principle by analyzing changes in pressure and velocity. I have also compared simulation results with theoretical values to evaluate the accuracy and limitations of this method. Theoretical background. Bernoulli's equation explains how pressure, velocity, and height interact in a steady, incompressible flow. According to this principle, when velocity increases, pressure decreases, and this concept is key in understanding how lift is generated over an aircraft wing. In this simulation, we are going to use this equation as a benchmark for comparison. Simulation setup. The simulation was performed using a simplified model of Cessena 172 placed in a virtual wind tunnel. Air was modeled as the fluid with a constant density of 1.225 kg per cubic meter. The inlet velocity was set to 23 meters per second and standard boundary conditions were applied to reflect realistic flow behavior. Mesh and domain. A refined mesh was created around the wing surface to accurately capture the boundary layer and flow separation. The overall mesh had sufficient resolution to ensure reliable results while maintaining the computational efficiency. This setup helped ensure accurate simulation of both velocity and pressure gradients across the wing. Velocity distribution. As you can see from the velocity contours, airflow accelerates over the upper surfaces of the wing and slows down underneath. This difference in speed is what Bernoulli's equation predicts, and it forms the basis for lift generation in aircraft. Pressure distribution. Here we observe the pressure distribution across the wing. The upper surface, where velocity is higher, shows a significant pressure drop. Meanwhile, the lower surface has slightly higher pressure. This pressure differential confirms the inverse relationship between the velocity and pressure, which supports Bernoulli's principle. While Bernoulli's theoretical pressure drop is approximately 600 pascals, the simulation shows a difference of around 280 pascals, which is quite reasonable, given real-world losses and assumptions made in ideal flow theory. While the simulation doesn't perfectly match theoretical predictions, it closely follows the expected trends. The discrepancies are likely due to viscous effects, turbulence, and minor numerical error, all of which are part of real fluid systems. Overall, the simulation confirms the conservation of energy and momentum in a flowing fluid as described by Bernoulli. In conclusion, this CFD simulation effectively demonstrates Bernoulli's principle in action. It shows that higher velocity regions correspond to lower pressure zones, which is foundation for lift in aviation. This project highlights the power of CFD in visualizing and validating core fluid dynamics and concepts. Thank you.